start off giving a refresher on how to do linear motion using kinematic equations.
And then I'll pick it up and say rotational motion, and then I'll explain the variables and how they relate to the kinematic equations.
And I'll go ahead and proceed, and I'll do the example and show you how all that connects.
And I'm doing editing. All right, so I'm gonna start off with a little refresher on how to use kinematic equations to solve for linear motion. So first off, there's 4 main kinematic equations, and it's these 4 right here. And all of these 4 equations have 5 variables in it. So first one is v initial, which is the initial velocity. The second one is vf, which is final velocity. Then it's change of position, and then it's acceleration, and then it's time. Each equation has 4 of these variables in it. Each equation has 4 variables each, and then you'll be given 3 variables each equation to solve for the 4th. And you'll know which equation to use based on which variable is not in the equation. So this equation right here does not have acceleration. So if there's a problem with acceleration in it, you will use that equation. This one doesn't have change of position. The third doesn't have final velocity, and the 4th doesn't have time. And that's basically how you know when you use these equations.
So now we will discuss chapter 10, rotational motion, and we're going to start with comparing linear variables with rotational variables. So essentially it's the same thing we use with the kinematic equations. This time, instead of linear motion, we're using angular motion. So delta x will be equal to delta theta. Time is the same. Velocity is now omega. Acceleration is now alpha. Mass is now moment of inertia. Force is now torque. And momentum is now L. And so, along with new variables comes new units. So now we'll be working at radians, and then the time is still the same. So we'll be radians per second squared, so on and so forth. And so, and also for kinetic energy, it's not translational anymore, it's rotational. And we know if something has rotational motion, if it's moving in a circle. And so our example coming up in a little bit, you'll see rotational motion. And so for the kinematic equations, we have omega equals omega initial plus alpha times time. Theta equals theta initial plus omega initial times time plus 1/2 alpha times squared. Omega squared equals omega initial squared plus 2 times alpha delta theta. In some cases though, they may give you the final theta or initial theta. That's why it's better to just write them out. Theta equals theta initial plus omega t minus 1/2 alpha t squared. And then another thing to note about theta is measured in revolutions. And so in the problem they may say revolutions, then they're referring to theta.
A fidget spinner rotating with a constant angular acceleration turns through 61 revolutions during a 5-second time interval. Its angular velocity at the end of its interval is 53 radians per second. What is the angular acceleration of the fidget spinner? Okay, so in step 1, we need to find out which equation we need. And what we already know is, we know the revolutions, we know the time, we don't know the angular acceleration, but we do know omega. So this is the equation we're going to use. And we're going to subtract initial theta from theta on this side so we can get delta theta. So that's going to turn out to look like this. So now step 2. We're gonna see what was given. And so what we're looking for is So what I'm doing is I'm converting the revolutions into rads. But now I know time equals 5 seconds. Omega is 53 rads per second. Now we just have to figure out what the angular acceleration is. So that goes to step 3. We gotta now manipulate the function, the equation. So the angular acceleration equals over time squared. So now we have this equation to find the angular acceleration. Now we're just going to plug in all the variables. That's a 2, by the way, my bad. That's what I see. And that's how we find the angular acceleration.
So this concludes our presentation. Just to recap, we started with the kinematic equations and then we transitioned into the angular motion. And the way we did that was by substituting the linear variables for the rotational variables. And then we went to our angular motion and how that relates to anything spinning. And then we finished by doing an example with the fidget spinner and talking about how we find the angular acceleration using one of the 4 kinematic equations for rotational motion. A few key things you should look out for is sometimes the problem, as in the example we did, it give you the delta theta in revolutions. That should always be in radians. As so the velocity and the acceleration, they should always be in radians. Other things, problems would probably have is time would be in minutes or hours. They should always be in seconds because that goes along with the units for angular motion. And so keep a lookout for those things, and we hope you enjoy our presentation on angular